Good morning, everyone. My name is Kalin Gochev. I'm a PhD student at the University of Pennsylvania, and today I'll be talking about incremental planning with adaptive dimensionality. And this is joint work with my two advisors, Dr. Stefanova from the University of Pennsylvania and Dr. Gochev from Carnegie Mellon University. So first I'll begin my talk by giving a brief introduction and an overview of our existing algorithm for planning with adaptive dimensionality and how it works. And then I'll go into the novel thing about this work is the novel way of doing incremental weighted A-star search, which we call tree restoring weighted A-star. Then I'll go into our experimental setup and the results that we observed, and I'll conclude with a brief summary and future work goals. So first, planning with adaptive dimensionality. So the motivating assumption behind this work is that in many high-dimensional planning problems in robotics, the high dimensionality is not necessarily needed everywhere in the search space. So a lot of time, low dimensional planning is sufficient for large areas of the environment, and high D planning is necessary only in certain regions. So for example, if we have a car-like robot that needs to navigate from point A to point B, the plan path is mostly straight line segments, and which suggests that we don't really need to worry about the heading of the vehicle. But in areas that require turning, like the ones in the red shaded circles, we need to worry about system constraints such as minimal turning radius and things like that. So this is where we need the high dimensional planning. So some related work so there's the main approach to kind of reducing the dimensionality of the problem is to do low D global planning coupled with high D local planning, which is the most common approach in robotics. Another way to kind of think about reducing the dimensionality of the problem is if you're doing pre-computing very accurate heuristics by solving a low dimensional version of the problem and then using that to kind of help a high dimensional planner to come up with solutions quickly. And also there's other ways to kind of reduce the size of the state space by grouping states in pre-computing costs or through state abstraction. Our approach differs from these in the way that we group states. We're grouping them by projecting them down into a suitable low dimensional space rather than combining adjacent states, for example. So how does planning with adaptive dimensionality work? Well, the idea is to decompose the high D planning problem into a series of graph searches in a hybrid state space that contains both low D and high D states. So to do that, we need to have a suitable low-dimensional projection of the high-dimensional state space and a projection function lambda that allows us to kind of map states from the high D to low D and vice versa. The important restriction here is that the low D state space needs to be optimistic in a way that it always underestimates the true cost to go in the high D state space. So for example, we have an optimal path between x and y in the high D state space, that its cost needs to be at least the path of the optimal path between their low dimensional projections x prime and y prime. So we then are going to iteratively construct and search a hybrid state space, which initially is identical to the low dimensional state space. And then at each iteration, we're going to search this hybrid state space, compute the least cost through the hybrid state space. Then we construct a tunnel around the path that we compute in the hybrid state space. We're going to search completely high dimensionally only inside this tunnel, which is a subgraph of the high dimensional state space, but it's a much smaller subgraph, so we can search that very quickly. If we successfully find a path through the tunnel, then we're done. Otherwise, we need to introduce more and more high D regions into the hybrid state space. So here's an example for 3 DOF navigation planning for car-like robot. So high D states contain both positional information, x and y, and also information about the heading of the vehicle. And low D states only contain positional information. So initially, our entire space is low D, and we are tasked to navigate from the start on the top left to the goal on the bottom right. Then initially we have 2 high-dimensional regions around the start and goal. So if our start and goal states are specified in high-dimensional configurations, we need to make sure they're actually part of our graph. Then we're going to search this hybrid state space for a path. And notice the smooth turn transitions in the high D regions that obey constraints such as minimal turning radius and the simple 8 connected transitions in the loading space. So now we're going to construct the highly tunnel around this path and only search in the high dimensional space only inside the tunnel. And this time we get stuck trying to make the turn on the top right corner. So this indicates that we need a high dimensional region there. And then we proceed to the next iteration. Again, we search this hybrid state space, we find the path, we construct a tunnel around it, we search through the tunnel, we get stuck on the bottom right, on the bottom left. Then we add a new high dimensional region, then we search again, construct a tunnel. Finally, we're able to compute a fully high dimensional path within this tunnel. And we're done planning. Okay, so what are the strengths of our algorithm? Well, firstly, we're performing highly planning only where it is strictly necessary for the problem. If we have pronounced local minima due to the heuristic function, we're expanding these local minima in the loading space, which is significantly fewer states than if we had to expand the local minima in Heidi. And last but not least, our algorithm provides strong theoretical guarantees such as completeness with respect to the original Heidi space and Balaton solution costs of optimality. So here are 2 examples of applications of planning with adaptive dimensionality. On the left is the PO2 robot doing a 3D navigation planning through a cluttered indoor environment. As you can see, I guess you can see really well. Here we have Heidi regions inserted in challenging areas such as narrow passages and near doorways, where we do really need to worry about the Heidi planning. And on the right is 11 DOF mobile manipulation planning. Here our full 11 DOF state contains the 7 degrees of freedom of the arm, the base position and orientation, and the torso lift. And the robot is tasked to maneuver this 80 centimeter long stick through this 50 by 40 centimeter window. And the planner this time introduces a Heidi region near the center of the window where it really thinks Heidi planning is necessary. Also the low-D state space in the 11 DOF problem is actually just 3D XYZ position of the end effector only. So we're doing quite a big dimensionality reduction in this case. So our algorithm searches hybrid state space at every single iteration. So starting this search from scratch at each iteration is very wasteful as it leads to many redundant state expansions. So a suitable incremental graph search algorithm can improve performance significantly. So what are some of the things that we need to consider when we're thinking about the suitable incremental graph search algorithm? Well, changes in the graph are very local. So we're only changing the graph inside these newly inserted Heidi regions. Also, the new regions are usually inserted closer and closer to the goal state, which means larger and larger portions of the tree that we've generated during the previous search iteration remain valid and we can reuse them. And also, last but not least, edge costs only increase since the low-D state space is underestimating the cost when we insert a Heidi region, actually increasing the cost of that region. So our original heuristic remains consistent, so we don't need to worry about recomputing it at every iteration. So some of the common incremental graph search algorithms. So there are mainly 3 classes of incremental graph search algorithms. The first class is aiming to improve the heuristic between search iterations so that this particular search iteration is done much faster. And examples of these are adaptive A-star and generalized adaptive A-star. Then the second class is they aim to repair and identify and repair inconsistencies in the search tree. And these are the incremental A-star, D-star, D-star light, and anytime D-star. They're very general algorithms in the way that they work on any graph and can handle any edge cost change, so increasing and decreasing edge costs. But for example, D-star light, when you have an increase in the edge cost, it needs to expand many states twice in order to correctly propagate the inconsistencies of the search tree. And the third class of incremental graph search algorithms, instead of repairing the inconsistencies in the search tree, they just aim to identify the largest unaffected portion of the search tree and just resume searching from there. And these are differentiating A star and differential A star. And our algorithm falls into this category. It's very similar to differentiating A star. Its idea is very similar to differentiating A star. But differentiating A star only works on 2D grids with unit edge costs, which is a very limited assumption for the algorithm. And it's very simple to implement, and it's much less complicated than differential A star. And it also allows for doing weighted search in a way that we can trade off solution quality for faster planning time. So what's the idea behind tree restoring weighted A star? Well, we're going to keep track of the state of the search. And by the state of the search, we mean the contents of the open list, the closed list, the g-values, and the parent pointers for all the states that we've seen so far. And each time we expand the node, the state of the search changes, which gives us a nice notion of time and progress of the algorithm. So we're going to keep track of a discrete time variable, t, that we're going to increment after every expansion. So then, given a set of modified states, we want to identify the latest time Tmax at which our search tree was still valid with respect to the modified states, and be able to very quickly restore the search state at time Tmax and just resume the search from there. So here's a quick example. So this is a very simple graph. We're trying to find a path from S to G. And for each state, we're going to keep track of three things. The creation time of the state, the first time we put the state on the open list. The expansion of the state, when we expanded the state, took it off the open list and put it in the closed list, and a history of parents. So at time 0, the only state we know about is S. It's created at time 0, and it doesn't have any parents. So at time 1, we expand S and create two new states, A and B, with parents S. Then let's say we expand state A. Then this creates one new state, state C, which is created at time 2, and its parent is A. Then let's say we expand B next. This creates one new state, D, which is created at time 3, but also let's say B is better parent for C than A was. So we need to update the parent of C to be B, but we will also remember that A used to be a parent of C. And then we expand D, we get to the goal. Let's say the edge BD changes cost, so its cost increases. So this edge was first considered at time 3 by this search. So if we restore our search state to time 2, right after we did the second expansion, then we can just resume the search and it will take into account the new edge cost. So now let's consider the two states D and G. At time 2, these states have not yet been created, so they should be unseen by the algorithm. States S and A, on the other hand, they have been created at time 2, and they also been expanded at time 2, so they must be on our closed list since we have already expanded them. And then B and C, they have been created but not yet expanded at time 2, which tells us that they must be on the open list. Also, the B cannot be a valid parent of C at time 2, since B has not yet been expanded at time 2. So this tells us that we have to go through the history of C and find A as the valid parent of C at time 2. So when we effect all these changes, we get this state of the search at time 2. And then resuming the search from here would just take into account the increase in edge cost for the edge B and D, and we'll find a new updated path to the goal. So what did we need? We needed to keep track of the creation time of each state, the expansion time of each state, and the history of parents. And with this information, we can restore the search state at any previous point in time. This introduces some memory overhead, as we need to store two ints and a list of pointer and an int for each state. But the list of pointer and ints should be fairly small if your graph doesn't have a huge branching factor and your heuristic is pretty good. So the heuristic will lead you to find a pretty good parent for each state right off the bat, and then you won't be finding better parents that often. So the history should stay reasonably small. Okay, so what are the theoretical properties of tree restoring weighted A star? Well, it behaves just like weighted A star. You preserve the same theoretical properties of weighted A star algorithms. So correctness, completeness, balance, solution cost, and optimality, all that applies. It handles only increasing edge costs because we're not recomputing the heuristic. But this is fine in the context of planning with adaptive dimensionality because for planning with adaptive dimensionality, we're only increasing edge costs anyway. It identifies the latest state of the search that is still valid, which says that it performs really well with local graph changes that occur closer and closer to the goal. So we have larger and larger portions of the search tree that we can reuse. And also, it never expands more states than starting weighted A star from scratch. So here's an example when we apply tree restoring weighted A star to planning with adaptive dimensionality. So in this example, the robot needs to navigate from the start state on the left to the goal state on the right through this indoor environment. And we don't use a heuristic just for illustration purposes in this example. So during the first iteration, we're doing a bunch of ID expansions near the start state, and then we expand the rest of the environment and load it. Then, during our tracking phase, during the tunnel search, it identifies some region that we need to do high-dimensional planning for, and it introduces a new high-dimensional region, which is the set of modified states. So, this is what our open list looks like at the end of the previous search iteration before we do the tree restoring. Then after we do the tree restoring, the search frontier is retracted right to the time right before it got to the modified region. And then resuming the search from here, we expand much fewer states than if we were to perform the entire search from scratch. And then again, during the next tracking phase through the tunnel search, it identifies a new region that needs to be high D. Then tree restoring retracts the search frontier back to right before that region was encountered. And then finally, we're able to find a complete path to the goal. So for our experimental setup, we chose 3 degree of freedom XY heading navigation for the PR2 robot, performing full body collision checking through cluttered indoor environments. And we used non-holomorphic vehicle constraints, which is to say, even though our robot is capable of turning in place, we enforce minimal turning radius constraints. So it's more like a car-like robot. This makes the search problem a lot tougher, as it needs to figure out complicated maneuvers in a way to kind of squeeze in between narrow tunnels and things like that. So we compared 5 different planners: 3 degree of freedom weighted A star lattice planner, the non-incremental version of our adaptive planner, and 2 incremental versions, one using the tree restoring weighted A star algorithm and one using incremental anytime D star. And also we compared against a 3 degree of freedom bidirectional RRT planner, which is a sampling-based approach. We had 30 cluttered indoor environments with varying degree of difficulty. And we performed full body collision checking against all 3D states, which was extremely computationally expensive. And for 2D states, the adaptive planners used much simplified and cheaper collision checking against the 3D map. So here are the results that we observed on the 30 cluttered indoor environments. The RRT results are averaged over 10 runs on each scenario, so we have a total of 100 runs for the RRT. And we can see also the high planning times are due to the expensive collision checking that we perform. We can see that the tree restoring incremental adaptive planner performed the best of all 5. Also, the RRT's performance suffered significantly due to the many narrow passages in our maps, such as doorways and gaps in between furniture. So, yeah, tree restoring weighted A star performed the best. It actually outperformed anytime D star adaptive planner, which suggests that tree restoring weighted A star is a better incremental search alternative in the context of planning with adaptive dimensionality than using anytime D star. These results are only on the 18 scenarios that require more than one iteration of planning, so these are the tougher scenarios. And these kind of are to split apart a bit the performance of the three adaptive planning algorithms, because on scenarios that only require one iteration of planning, all three perform identically. So we can see here that, again, the tree restoring weighted A-star adaptive planner performed the best. Also on the right here we have the time that the planning phase took, so the search through the hybrid state space, which is the incremental part, which is the part that we made incremental. So the search through the tunnel is not incremental, and here we only compare the search through the hybrid state space. Here we can see that the planning phase actually improves by a factor of 3. And this is a plot of the average speed up factor that we observe between the tree restoring weighted A-star and the non-incremental adaptive planner as the number of iterations or the toughness of the problem increases. So we can see we get much better speed ups as the difficulty of the problem increases. So in conclusion, tree restoring weighted A-star is a general weighted A-star algorithm. It handles only increasing edge costs. It is most useful when changes are close to the goal, and it allows for suboptimal search, which is trading off between optimality and planning times. It's very simple to implement, and it has relatively low overhead. Also, it lends itself very nicely into the context of planning with adaptive dimensionality and increases the performance of the planning phase of the algorithm by a factor of 3. Also, we observe very similar performance results for the domain of 11DOF planning for mobile manipulation. I guess I'm running out of time, so I'll skip the future work and go straight to questions.